Welcome back to GFE0007 Data Analytics Made Easy for Beginners, and today we'll be discussing week 4, which is on Introduction to Predictive Modeling. Now let us first look at our roadmap for today, and we'll start with part 1, which is to define what a model actually is, and then we want to establish our core vocabulary. And then in part 2, we will discuss the supervised segmentation, which is the central idea of dividing the populations into several groups based on a target variable. And then the third part will introduce to entropy and information gain, and these are the mathematical tools to measure which attribute in the datasets that contain the most useful information. And in part 4, we will learn about the tree induction, which is the process of building a classification tree automatically using the divide and conquer approach. And then in part 5, we will cover the probability estimation, and we will try to understand why by simply giving the label is not always enough for a business. So we'll wrap up with a synthesis on how all of this will tie back into the data analytic thinking. So let us open with a question to get you thinking about why we need to do the predictive modeling. I want to give you the mushroom problem. So imagine you are now hiking you are now hiking, and then you find a mushroom. So how do you decide if the mushroom is safe to eat? So naturally, you look at attributes such as the color of the mushroom, the shape, or even the smell. So basically, you are searching for the single feature that gives you the most confidence. And we know in nature, it turns out that order is extraordinarily informative. So if it smells like food such as almond or anise, then we can say that the mushroom is almost certainly edible. But if it smells foul or musty, then we know that it is almost certainly poisonous. So similarly in data science, we do the exact same thing. So instead of just using our intuition, we use mathematics to systematically analyze thousands of examples to build the predictive machinery. So let us look at the real-world business problems that require this kind of approach. So first, we look at the customer churn. So take one example of a telecom company. This telecom company may have like 20,000 customers with expiring contracts, but only enough budget to call 2,000 of them. So who should they call to prevent them from leaving? And then we look at the second example, the credit write-off. So this one is from a bank. So let's say a bank must use the historical data to decide who among their customers might be too risky to receive a loan, who they would want to give the loan, who they try to avoid, or they would reject the loan application. And the third one is on the fraud detection. So let's say there are millions of daily transactions. So how do you know which small fraction are actually fraudulent? So the common thread here is that we cannot directly observe the future outcome. For example, we don't really know with certainty whether the customer will leave, whether this transaction is fraudulent. So we must infer it from the data that we have. So in other words, we must infer it from the observable attributes. So that would be the essence of predictive modeling. So the first part is on the model, induction, and prediction. So first is, let us define what does a model means. By definition, a model is a simplified representation of reality which is created to serve a specific purpose. So the model will abstract away irrelevant details, and it only keeps what matters for the task at hand. So think of a road map. Okay, so it keeps road and destination but discard individual buildings and terrain, because what you focus on is the road that will help you to navigate where you want to go. So another example is architectural blueprint. They keep the layout, but they discard the specific materials, because the most important thing when you look at the architectural blueprint is the layout. So similarly, the credit scoring formula only keeps the account attributes that predict the default, but they may discard all other variables or all other observations that are not important to help you to predict the default status. So the key insight here is that a model does not need to be true, or the model does not need to be perfectly represent every atom in the universe to be useful. It just need to be good enough for its specific purpose. So now we distinguish between the predictive and descriptive model. So what is the difference? On the left-hand side, the predictive model aims to estimate the unknown target value for a new and unseen case. So we judge this predictive model by its accuracy on the new data. For example, this customer has 78% chance of churning. And we do this predictive, how do we know this figure? Is that we look at the historical data and we know that customers who have similar attributes, they are more likely to churn. On the other hand, the descriptive model is meant to help us understanding the underlying patterns and to gain insights from our data. So we judge this by how intelligible and explanatory it is. For example, customers who churn tends to have high overages. So these are not mutually exclusive. A good predictive model often provides a deep descriptive insights also. And next is we look at the difference between classification versus regression. So in classification, the target is a category or it's a class label, like churn, not churn, spam, not spam, edible, poisonous, yes and no. So the model assigns an instance to a class. For example, you look at this customer profile and then you categorize these customers to be defaulters or non-defaulters. And then we estimate the probability of the membership. For example, like for this particular customer, the probability of this individual to be defaulting is 80%. So we put them into the category of defaulting. So the regression, on the other hand, deals with numerical target. For example, like predicting the next quarter's revenue, or predicting the house price, or the units sold. So while regression measures impurity through variance, so this lecture only focus on classification because it is incredibly common in business, and then sometimes it often gets less coverage in traditional statistics course. Now let us learn the language of data science so that we are all on the same page. So what does it mean by instance? The instance is a single data point, like one individual customer or one mushroom. Okay, it can be individual, it can be a human, it can also be a thing. So a feature or attribute is something that is measurable property of the instance, like based on this customer, or based on this mushroom, what is the color of this mushroom? What is the age of this customer? So this is the feature or attribute. Usually the instances are sorted in row and the feature and attributes are in columns. So the target variable is the specific thing that we want to predict. So the target variable is, for example, like individual income. So this is something that we want to predict. And the other variable that we use as the to predict this income is what we call as the feature. So the feature can be someone's education and age. So you know when they have higher education, then it is more likely that they have higher income. And age is also another feature. The higher the age, the higher the income will be, because when you work longer, then your salary will also increase. So what is the training data? So the training data is the historical data that we use to build the model, and the process of building that model is called induction, or we also call it as learning. And then when we apply the model to a new data without the target variable, we call this as prediction or inference. And now we want to differentiate between induction and deduction. So deduction starts with general rules to derive specific facts, like all men are mortal. So Socrates is a man, therefore Socrates is mortal. So that is deduction. So induction, on the other hand, it works the opposite way. It starts with a specific example and then it generalizes them into rules. For example, if this mushroom has a foul smell, then we consider it as poisonous. And then if we find another mushroom that is also foul smelling, then we categorize them also as poisonous. And then from here we induce the rule that foul odor predicts poisonous. You have to remember, in data science, prediction is not just mean the future. It also means estimating any unknown value, whether it happened in the past, present, or future. So when we say that using historical data to predict the future is, for example, like we are using the historical data from several days ago to predict whether today will be raining or not raining. But we can also predict, for example, if I have a group of workers and I look at their age and I look at their education and then I try to look at their income. So when the new person come in, I can predict this new person income using the age and also education level. So it's not just always about the future. Now let's talk about supervised segmentation. So the central question is, can we divide a population into several groups that behave differently regarding our target? For example, if our target is, we have a certain target. So can we divide this population into several groups, 1, 2, 3 or more groups based on this target? So if we can, then we can predict the target for a new case by assigning them to the most similar group. Let's take an example, okay? So let's say we have a segment of individuals and these are the middle-aged professional in New York City with high overages. And then we might find that they have a 5% churn rate. So let's say there is a new customer, and if this new customer fits that description, then we would predict that this person would have a 5% of probability to churn. Next is, we want to understand what makes a segmentation useful. And here we talk about purity. Purity is like how accurate it is, how pure it is, how pure is the segmentation. So imagine this, if we can meet in a physical classroom settings, yeah. And then I try to divide you based on several attributes. So maybe I can choose based on gender, based on age and all that. So it might be that this segment are all female, young women, okay, young women segment, and the other one is old woman section. The other one is young men and old men. So the purity will tell me that from one segment to another segment, they are significantly different based on the target variable that I have. So a segmentation is useful if the group are pure, which means that almost all of the members would share the same target class. So let's say if 8 out of 8 people in a group are write-off, then that group is perfectly pure. And then the entropy would be 0 because it covers all of the people in that group. On the other hand, the impure segment is more mixed. Like for example, in this segment, we have 4 and 4 write-off and 4 is not write-off. And this will give us an entropy of 1 and there's no predictive power. So our goal is to find the attributes that divide the population into groups that are as pure as possible. So we have a we have seen the example with the 12% data sets. So we have attributes like the shape of the head, the shape of the body, and the color. So the question is, which one best separates the write-off from the non-write-off? Well, you might want to debate about it. In these specific data sets, the body shape produced the purest subgroup. Now let's talk about the challenge of scale. Okay, so for example, if you only look at 3 attributes and 12 instances, then our eyeball are able to look at specific attributes that make individuals or within each segments different. However, usually when we look at the database, for example, the marketing database, they may have more than 400 attributes and probably 2 million records. So in this case, we are not able to see the patterns with just by looking at the data set. Instead, we need a systematic and quantitative method to measure how much each of the attributes reduce this uncertainty. And this is where we formalize the term of uncertainty using what we call as entropy. Now let's talk about entropy and information gain and what does it mean. So now I want you to think of a pirate treasure which is buried on a 10-mile island. So if the pirate tells you that it is in the eastern half, so you don't know the exact spot, but your uncertainty has been reduced. So in data science, a variable is informative if knowing the value would narrow down our uncertainty about the target. So the formal measure for this disorder or this uncertainty is called entropy, which is invented by Claude Shannon in 1948. So here is the formula for entropy, where entropy S is given by the negative sum of P, where P is the proportions of instances in class P, and then the P times log P. Okay. So the entropy will always range from 0 to 1, as you can see from the graph here. So entropy of 0 means complete certainty, or it also means there's a pure group where everyone is the same, while an entropy of 1 means a maximum uncertainty. So the perfect one is when we arrive here, which is a 50-50 split. Now let's look at this example. Let's say in a group of 10 applicants, there are 7 who would repay back the loan and 3 would default. So the probability of the non-write-off is 0.7 and the probability of write-off is 0.3. So the entropy in this case is calculated as a negative 0.7 times the log base of 2 of 0.7 minus 0.3 times log base of 2 of 0.3, which is, we calculated, it is approximately 0.88. Since 0.88 is closer to 1, so we would say that this group is fairly impure. So if, let's say, the group were 100% write-off, then the entropy would be 0. If it is like 50-50 mix, it would be 1. Now let's talk about the information gain or IG. So the information gain measures how much an attribute reduces entropy across the group it creates. So the formula is information gain of the parent and children equals the entropy of the parent minus the sum of the proportions of the child I times the entropy of child I. So we weight each child's entropy by its size because a split that cleans up a large portion of the data is much more useful than the one that creates a tiny pure leaf but would leave the rest messy. And then next is we compare the two attributes, which is balance and residence. So let's say if we split on balance, we get a large reduction in entropy with an IG of about 0.37. But if we split on the residents, it will result in much smaller reduction with an IG of only 0.13. So what would be the conclusion here? Balance is more informative attribute. So if you can only ask one question, then ask about the account balance instead of residents. Now let's look at this from the point of view of the mushroom data sets. So let's say we have 22 attributes, and then probably we have like 5,000 examples, and then we rank them by information gain. So order in this case is the winner because it has an IG of 0.86, meaning that by knowing the order, you eliminate 86% of your uncertainty about whether the mushroom is poisonous or not. So a weak attribute like cap shape may explain very little, and it has a very low IG. So now let's look at handling numerical attributes and the regression counterparts. So to handle numbers like age or balance, so what we do is we discretize them by choosing a threshold. For example, we put a threshold of 45. So if age is less than 45 or age is more or equal to 45, and then we test the different threshold to find the one that maximizes information gain. So for example, here we choose 45, and then maybe we can choose 44, 43, or 46, or 47, or even any other numbers. But basically, we choose the numbers that would maximize the information gain. So for regression, where the target is a number, we use the variance reduction instead of information gain. So the formula is given by the variance reduction is given by the variance of the parent minus the sum of the proportion of child I times the variance of child I. So the logic here is the same because we choose the attributes that would reduce the variations, the most variation. Now, we move from single attribute to using full model using the tree induction. So a real decision requires multiple attributes, not just one attribute. For example, if you want to predict someone's income, then you cannot just base on his education alone. So the tree induction is an elegant divide and conquer approach. We also call this as a greedy approach that builds multi-attribute models. So it can handle hundreds of attributes, and then it also produces human-readable if-then rule. If-then rules means that if someone is middle-aged and professional and working in New York City and high averages, then the churn rate is 5%. So this tree induction can also be scaled to millions of instances. So now let's look at the anatomy of a classification tree. So we start with the root node, which is on the top one here. And this is the first test which all the instances will pass through. So imagine if you have like 1 million instances. So all the 1 million instances will be here first before it is being filtered through the leaves. We call this as leaves. So for example, the first one is the root node is asking whether this person is employed or not. If it is yes, then we go to the balance. Is the balance is more than 50K? And then if yes, then we can classify this person as write-off. If not, then it is not a write-off. Okay, if the person is unemployed, and then we look at the age. If age is above 45, then write-off. If not, then it is non-write-off. Now, let's classify a customer, and let's say the customer's name is Claudio. Okay, So let's say the Claudio is not employed, and then he has, I'm not sure whether it is a he or she. So this person has 115K in his account, and he's 40 years old. So how do we do the prediction? So first is we start at the root. We ask the question, is he employed? No. So we take the right branch here. No, not employed. And then we want to ask if his age is less than 45. Yes, because he is 40. And then, so we take the left branch. And then we land on a leaf that predicts as a non-write-off. So in business term, Claudio belongs to a segment predicted to repay their credits. Next is we want to look at the tree induction algorithm. Okay, so this algorithm is a recursive process, and it starts with all training examples, and then we compute the information gain for every attribute, and then we choose the one with the highest IG to split. What does it mean by split here is, for example, the employed is split into 2, yes and no, and balance is split into 2, whether it's less than 50 or higher than 50K. Okay, and then we repeat the process for each subset created, and then we only stop when the subsets are pure or we meet another stopping criterion. So let's look at the tree induction from the point of view of the stick figures. This is a step-by-step approach. So first split is we use the body shape, which have the best information gain. And for the oval group, split 2 uses the head shape to create pure leaves. And for the rectangular group, the third split or split 3 uses body color to create the final pure leaves. So the result is a complete tree that perfectly classifies all the 12 examples. Now, we can visualize all this in using the instance space. So each node draws a decision boundary. So this is what we call as the decision boundary. First is we look at the balance, and then we divide the balance into 2, which is 45K. This is less than 45K, this is larger than 45K. And after that, for those with a balance of larger than 45K, then we look at the age. Not 45, sorry, it's 50K. And then now we look at the age. So if the balance is larger than 50K, and then we look at the age, whether or not the age is less or larger than 45. Now we see how the trees translate into if-then business rules. So every path is a rule. Like this one, we have, for example, 4 paths here. So if balance is less than 50K and the age is less than 50, then write off. Okay, and then these are all the rest of the rules. And the rules are great because then we can debate and we can act on them without needing to be a data scientist. In a highly regulated industries, for example, like in banking, the ability or the explainability of this model is often a legal requirement, because sometimes there are some machine learning technique, for example, like the neural network, which is highly the algorithm is done within the black box, so you don't really know how the prediction is being made. And if, let's say, you want to justify the decision that you made, it will be very hard for you to do so, because you don't know the how the algorithm working, what is the rules that is being employed within the black box. But for the tree analysis like this, it is very easy, and it is very easy for you to justify whether or not you want to take one decision or another. So let's look at this example. This is a case study which is the churn prediction tree involving 20,000 customers. So we rank the attributes and then we find the home value has the highest information gain, which is likely as a proxy for financial stability. So we build the tree starting with home value at the root, and then one important note here is that we stop the tree before it creates 20,000 leaves to avoid from overfitting, which is when a model memorizes data instead of learning general patterns. So what it means by overfitting here is that we can try to be highly accurate as possible, but we also want to achieve some generalizability as well. Okay. Now, let's go to the fifth part, which is on the probability estimation. Now, let us answer this question. Why not just predict the class? Okay. In a credit problem where usually only 3% is defaulters, even a high-risk group might only have like 15% default rate. So a binary classifier would just label everyone as not write-off, which is not helpful for a lender. So we want a probability score so we can rank the applicants from the highest to the lowest risk. Whenever the cost for different error vary, the probability estimate outperforms simple labels. And so we introduce the probability estimation trees. So the process is the same, but the leaf may now contain a class probability rather than a label. So let's say if a leaf has n positive and m negative instances, then the frequency-based estimate, which is the p hat of c, equals and divided by the sum of n plus m. But in this case, small samples are a problem. For example, when you have a leaf with only 2 instances that are both write-off, would give a probability of 1.0, just like a leaf with 200 write-off. So to handle this, we use what we call as the Laplace corrected estimate, which is p hat of c equals the sum of n plus 1 divided by the sum of n plus m plus 2. So in this way, 2 positive out of 2 give a 0.75 probability, while 20 out of 20 gives about 0.955. So in this case, larger samples would get more confidence. So these probability scores may help to unlock many business actions. So the telco companies can call the top end as most at-risk customers, and then banks can set interest rates to proportional to risk, and so the probability score, it would be an input cost-benefit calculation to find the optimal business policy when it comes to decision making. So let us summarize this. I know the last part, especially the tree induction, might be a bit technical for some of you. Okay, let us summarize our end-to-end workflow. Usually we start with the business problems, and then we collect the labeled data, and then we select informative attributes which is using information gain, and then we induce a tree model, and then we estimate the smooth probability, and then finally we take the business action. So we see what carries forward. So the concept of informative attributes can be generalized to all model, and then we'll dive deeper into overfitting and model evaluation in the future chapters. Okay, so the rest of it is this is some of the common misconception. For example, if you have like 73% of accuracy, this is not necessarily a good model without knowing what would be the best rate. So the most informative attribute, okay, globally is usually at the root, but ranking can change as you go deeper into the subsets. And also you have to remember that when we talk about the term prediction, so it includes estimating the past or present unknown values and not just about the future. Okay, so there are several concept check for you to enhance your learning, and this is some of this week assignment. You don't have to submit this, but I think it would be good for your understanding, so probably you can answer these questions. And this is some of the key formula which I don't think I will want you to really understand this, but this is just a quick reference. Okay, thank you.